This is Qixing. I'm going to present our CVPR oral paper this year titled Latent Diffusion of 3D Shape Geometry Models by Enforcing Geometric and Physical Priors. Diffusion models have generated great success in image and video generation. Standard diffusion models require ambient space with finite dimension. Because of that, they found limited application for 3D shape generation. 2 years ago, Latent Diffusion came out, which combines a representation-free latent diffusion and a representation-dependent decoder. Latent diffusion generated a lot of follow-up work in 3D shape generative modeling, which combines the implicit shape decoder and latent diffusion. Still, the other approaches still present various issues in physical stability and geometric fidelity. We can understand this behavior from the fact that latent diffusion essentially only uses latent codes of the training instances, which are sparse. However, if we have a shape decoder for any latent code, we can evaluate its quality starting from whether the shape is connected to more sophisticated issues such as physical stability and geometric fidelity. The goal of our work is to enhance the diffusion model using this quality checker, which assesses all latent codes. Conceptually, our work is related to guided diffusion. However, these approaches have limitations in they provide the trade-off between diversity and quality because they apply to the sampling procedure and they require the gradient of the classifier. In contrast, we convert the quality checker into a continuous function of the latent code and use this function to improve the diffusion network training without using its gradients. Our approach on the EDM framework, which has a principal way to determine the hyperparameters and the network representation. In our setting, we have two terms. One comes from the data distribution, one comes from the quality checker, and we want to determine the hyperparameters lambda t sigma here. To begin with, we started with a simple example of feeding x star to two sources with variance. If we want to minimize the variance of x star, then we know that the ratio between the coefficients is inverse proportional to their variance. In our setting, we use a similar result in which when optimizing each term in isolation, then d theta is linearly correlated with a gradient of log p. Because of this, we can quantify the variance using the ground truth distribution as a surrogate distribution. For the discrete data distribution, this is the result, and it is justified empirically. For the quality checker, because it's continuous, the behavior is very different. Result, we have the principal way to determine the trade-off parameters at different sigma, and we integrate this into the EDM framework to determine all the hyperparameters, and those we call the EDM when quality checker is not used. Our approach has two quality checkers. In terms of physical stability, we run worst-case structural analysis to determine the physical stability score of a shape. For geometric fidelity, we learn neural networks to predict its quality checker by using human labels. Our approach improves the state of the art in terms of FID and KD scores in the range of 10 to 20%. In terms of physical stability, our approach reduces the gap of the physical stability scores of training shapes by 40%, and hyperparameter optimization accounts for 30% of improvements. With the improved diffusion network, we have improved the text contingent 3D shape generation and improved the image condition results. I'm looking forward to talk more about our work in the oral session and in the post session, both on the first day of